Okay, so we will get started in just a bit. I'm just launching the live stream. Here we go. Okay, so it's 1 minute past. So welcome everyone again to the Topos Institute Colloquium. This week we have Florian Rabe speaking to us about MMT, a uniformal approach to knowledge representation. So thank you very much for accepting the invitation, and Florian, whenever you're ready.
Okay, thank you. So let me start by saying that, so we just talked about the mass folder project. You could say that we've been doing mass folder for the last 20 years already. And we're still falling way short of even the basic goal of the project. So it's an incredibly difficult and fascinating topic where it seems like we're never going to run out of problems to study. When I say we, I mostly mean Michael Kohlhase and myself. Kohlhase is my PhD advisor with whom I've been working on and off for the last 15 years. We've kind of divided the research group a bit, with him taking care more of the informal natural language side of mathematics and me taking care of the formal logical aspects. MMT is a system I built in my PhD thesis and that I have constantly refined ever since. And it has gradually taken over the entire research group. So nowadays, every student in the group is in one way or another working with the system. It's deliberately designed to be extremely flexible. So whatever interests the group develops, MMT is going to come in handy. It's a great system for rapid prototyping. So whatever one-off experiments one of our students wants to do, say develop some domain-specific language, parse the material, and then send it to some theorem prover, then MMT is a great platform to put that together relatively easily. Let me tell you a little bit about myself before I dive into details. I'm mostly interested in the theoretical foundations of computer science and mathematics, with particular interest in knowledge representation. And here I'm taking a very wide view. I'm interested in any kind of knowledge that can be formalized. So languages for formalized mathematics, to me, have the same status as programming languages, specification languages, ontology languages. They're all just formal knowledge representation languages. And MMT is filled with the long-term goal of integrating all of those and supporting all of those in one system. I'm interested not only in the foundations, but also in developing applications, mostly from the perspective of how can we build large libraries of formalized knowledge. It's usually a huge difference between coming up with a prototype implementation and actually supporting large-scale development in that language. And from a perspective of system integration, especially when you take such a wide view of languages, you're never going to be able to support everything in one system. So you need to seriously think about how can you make very disparate systems work together in some reasonable way. I tend to focus on breadth of methods. So I love abstracting from various systems that are doing different things, but applying similar methods. So like a theorem prover and a compiler, what do they have in common, and what kind of generic concepts can we abstract from there that we can then integrate into MMT as some kind of universal knowledge representation framework. Generally, MMT does not strive to make the individual systems obsolete. So MMT cannot compete with any particular theorem prover. Those are usually heavily optimized to prove stuff about one specific logic. Similarly, it can't represent any particular optimized compiler, which is heavily optimized to one particular programming language. It's meant to focus on the overall joint concepts that all these languages share. So We're calling this general goal UniFormal, like one universal framework for all kinds of formal knowledge. MMT is by no means a solution to that problem. It's more like a moving target. It's whatever we've understood, we capture in MMT, either at the conceptual or at the implementation level. So it keeps evolving and responds to whatever challenges we uncover. It's become quite mature by now. And it has relatively strong concrete applications that allow, for example, make it as easy as possible to prototype a new logic and then get, say, a type reconstruction engine and an IDE out of the box for that system. Skip these slides. I think I should say right away that I have a lot more slides than I can fit in 1 hour. So I strongly encourage you to ask questions to guide the talk into the direction you like, in particular when it comes to the trade-off between showing you nitty-gritty details about the syntax and semantics of MMT versus showcasing individual applications. So depending on what you're interested in, if you want to see the grammar and the type system, I have slides for that. If you want to see screenshots and demos, I have examples for that as well. One more overview of this slide. So the idea of MMT can be best understood with this 4-level hierarchy. The thing you're usually interested in is the actual domain knowledge. The domain knowledge. That's why mathematics is working basically exclusively. Then if you want to put that in a more formal setting, you have to invent a logic or some other formal language in which you write down your knowledge. Then you quickly find out that you end up with lots of different logics or similar languages, like just first order logic, higher order logic, modal logic. Already it explodes at the logic level. And that's kind of my home area. That's where my PhD was centered. So you have all these different logics and you realize, how can we relate them? How can we get some structure into this zoo of different systems? So you have to introduce meta languages in which you write down the individual logics, where you can then relate the logics to each other, maybe do things like logic translations or representation theorems across languages. In the area of logic, these meta languages are usually called logical frameworks. The system I've worked with most is the LF family of frameworks. Maybe you've heard of the 12th implementation, but they all work very similarly. You pick one particularly simple formal system in which you then represent the syntax and semantics of the actual logical systems you want to work with. But even there, we're struggling. First of all, well, the main problem with logical frameworks is that usually you want these languages here to be extremely simple to justify their existence as like the one and only meta language. But you also need them to be extremely expressive so that you can then represent all the various concrete languages you're actually interested in working with. And here the state of the art is not really satisfactory yet. Like, we have very nice logical frameworks, but they just can't represent all the logics that we need in practice. So we're constantly doing research about how we can improve our frameworks. And that means we constantly need to implement new frameworks. And that's where the idea of MMT came in. I wanted to implement my own logical framework, but I didn't really know which system that actually is yet. So I asked myself, can I implement as much as possible without committing to the concrete formal system I'm working with? If you think about how people implement formal systems, they usually start with a grammar and a type system, then they implement a parser and a type checker for those, and then they build stuff on top, like an IDE, module system, and so on. Which means the fundamental choices of which language you're working with are baked so deep into the system. If you later on decide you want to change your fundamental language a bit, add a new kind of type operator or something like that, most of the time you're stuck because it's just not possible anymore. You have to change so much code. You just can't do it, or it becomes a huge undertaking just to add features to your system. So MMT tries to turn that inside out, leave the concrete choice of formal system open, and implement everything else. In the beginning, that was just a research experiment. The question was, how much can we actually implement without committing to the precise formal system we're working with? And in my experience, that often has been up to 90%. Like if you think about the implementation work of a specific logic you've come up with, usually parser and type checker are relatively easy to do. And then you have to write a lot of code to have nice concrete syntax, to have an IDE, a module system, eventually, of course, then theorem provers, computation engines, and so on. But it turns out most of the work here doesn't actually depend on the logic. So the idea of MMT is to implement all the algorithms generically, and then later on inject the right rules to get the system you want. And before I go into the details, I have one more concrete slide when I say what I mean when I say all knowledge. We've recently come to understand knowledge as a kind of, we call it the tetrapolar structure of knowledge, where we have 4 different kinds of knowledge. So here we have all the logical languages, here are all the programming languages, data representation languages, which especially in mathematics are becoming more and more important, and natural languages in which we write down, especially in mathematics, a lot of content. So MMT is meant to sit in the middle of these, covering them all equally and allowing the interoperability across the different systems. Which means MMT mostly focuses on representing the joint essence of these 4 different extremes of how we can deal with knowledge. So MMT doesn't strive to be a theorem prover, it doesn't strive to be a compiler or a database engine. It focuses on representing the common concepts, the ontologies, the data types, which then allow mediating between the different systems. So I want to start with some concrete examples. This is a screenshot from the MMT IDE, showing you a hello world reformalization of propositional logic using the logical framework LF. This screenshot is just to prove that the implementation exists. It's didactically better to show you a slightly more readable example. So I talked about the 3 layers before: domain knowledge, logic, logical framework, and then on top of that, MMT. So that's what we are formalizing now. We start with the logical framework, in this case, LF. We were presenting it as a theory in MMT. The word theory is often called signature in other systems. It basically describes the fundamental constants of the language. So in the case of LF, that's a dependently typed lambda calculus. We have the universe of all types, the pi operator to build dependent function types, and the lambda and the apply operator to work with that type. MMT constants inside the theory are declared in the simplest case as name with optional type and optional notation. In this case, to get off the ground, we have constants that are declared without any type whatsoever, because we don't have any syntactic material yet that we could use to form types. So the only thing we do is we give them notations, at which point we already have a parser and abstract syntax trees for our language. So this is the normal pi and lambda notations. V is for variable, which means this position is a binding. Of course, we still need the semantics of LF. I can get to that later. That's where we have to inject rules into MMT that implement the semantics of LF. But let's assume we've done that already, then we can use LF as what we call a meta theory to define concrete logics. So in this case, we're defining some base theory that all logics can inherit from, using LF as the logical framework in which it is written. Now we can declare a type of propositions and a type of deductions for every proposition. So this uses a judgment of types paradigm where that F is the type of proofs of F. We can then extend this base theory by including it and defining other logics, such as first order logic, where we might add something like a type of terms, and then a universal quantifier.
Can I ask a question?
Using higher abstract syntax. Yes, please.
Can you say what the numerals are doing, like what the 1s and 2s
Oh,
do?
those are the argument positions to tell the parser in which order stuff will come.
So in dead down below, that 1, does that refer to any other 1s, or is it just
It's the first argument, meaning this one.
Ah, okay.
Yeah. This is copied from the previous slide, so it's just first order logic as before. We have so far only declared the syntax. Now we're extending that with proof rules. We have the default introduction rule and default elimination rule here as examples. All of this is relatively standard if you already know LF. If you don't know LF, then what follows is a mini tutorial for representing logics in LF. So the introduction rule for first order logic is meant to tell us how we can obtain a proof of for all x f of x, where f is an arbitrary predicate on terms. And we do that by proving for every x f of x. So if we have a function that takes an arbitrary x and returns a proof of f of x, then that justifies concluding that we have proved for all x f of x. It's a standard Curry-Howard representation of proofs as terms. And the elimination rule proceeds accordingly. So that's the second level. After defining the logical framework, we can use that to define individual logics in it. And this is just a tiny example to showcase the modularity. Again, this is copied from before. Now for the third level, using first order logic as a meta theory, we can now start formalizing some domain knowledge. In this example, it's the algebraic hierarchy. We start with a theory of magmas, where we have a binary operation on the terms, the composition operation, with its infix notation circle. And then we extend that in various ways, for example, to get a theory of semigroups, theories of commutative groups. And then one new thing we need if we want to do something like a theory of rings, where we need two binary operations. We cannot simply just include commutative group and semigroup because they're supposed to share the universe of terms, but this must be different binary operations. So we need a feature like named includes, like to compute a copy of commutative group and a copy of semigroup which we might call the additive and the multiplicative parts of the ring. And then we can do things like additive / comp to refer to the additive operation of the ring, and multiplicative / comp to refer to the multiplicative operation of the ring. And of course, in practice, you would add all better notations for these operations, which I've omitted in this example. So that exemplifies at the very simplest level how to use MMT. I'm seeing that people are asking questions in the chat. I had not noticed that before. Let me just check. Does MMT have a library of mathematics like Isabel or Lean or Misa? Yes, but again, MMT doesn't aim at competing with them. In particular, MMT doesn't have a huge library of proved theorems because MMT doesn't have the kind of theorem proving support that Isabel, Lean, and Misa have. But we have actually imported those libraries into MMT. That's something that comes on a later slide, so we can get back to that then. The big native libraries that are handwritten in MMT, that actually focuses on representing different logics, not so much different, not so much large libraries of domain knowledge, and that's what I'm going to come to immediately next. So this is like the library of MMT. The MMT library started with what we call the Latin project. That was a collaboration with Timo Sarkowski from Bremen, who maybe some of you know. And then the goal was to formalize all logics that exist in a highly modular MMT network of theories. So this was quite successful. It was the first major case study undertaken in MMT. Eventually, we had one huge diagram in the category of MMT theories. The diagram became so huge that we actually couldn't display it anymore properly. So at some point, we visited colleagues in Paris who had a 3 by 10 meter screen array. And for the first time, we were able to actually show the entire diagram. It gets so huge because of the principle that we state every single logical feature, like conjunction or universal quantification, in the smallest possible context, means everything gets its own theory. Axioms like excluded middle or choice, they're all segregated into separate theories so that we can then build the logics that we need by importing exactly the features that the logic has. So we got a huge diagram that was very difficult to work with. Here, for didactic reasons, is a tiny fragment of that diagram. So we might start with propositional logic, extend it to first order logic, but also to sorted first order logic. Then we have translations back and forth between those two. Sorted first order logic then is the basis to build higher order logic, where we basically have to add the function type operator to sorted first order logic. Higher order logic then has a semantics, where we interpret types as sets that we can write as a morphism between MMT theories into the set of C theory. Set of C itself is formalized by extending first order logic and adding the usual axioms of set theory. So you see at that point, the diagram does not commute. First order logic is both the basis to formalize set of C and a particular logic that gets interpreted in set of C. And we can, at this point, start adding the actual logics of standard proof assistants into the diagram. Something like wholelight is closely related to whole. The arrows are not here yet, but you can imagine it's like an inclusion error from whole to wholelight, which then gets translated into ZFC, and ZFC itself is slightly weaker than the set 0 of MESA, so we have another translation from there into MESA. But that's just the high-level view. If you zoom in, propositional logic isn't actually just one theory in MMT. It's written modularly with all features like negation and conjunction formalized individually, and then imported as needed to form the propositional logic we want. And then something like conjunction itself is not a single theory either. It's a triple of theories, one for the syntax, one for the proof theory, and one for the model theory. And that's the special case where you only formalized one proof theory. If you have a natural deduction calculus and a tableau calculus and so on, then you will actually end up with multiple proof theories here, and you can then represent meta theorems that relate those proof roots to each other as morphisms between the different formalizations of the proof calculi. In the hierarchy of different languages, this whole diagram sits at the logic level. And every node in this diagram serves as the root of a domain knowledge diagram. So for example, the library of MESA then is one huge diagram of theories, all using MESA as the meta theory. So in every node in this diagram, you can think of a huge library dangling underneath it for the concrete domain knowledge written in that logic. That brings me to the second major project we did. That was the OAF project. OAF stands for Open Archive of Formalizations. And there we attacked the problem of integrating all the big proof assistants into this diagram. So already indicated here that we have proof assistants in the diagram. And we can now take those logics, treat them at the base of a library like the entire wholelight library or the entire MESA library. So when we speak of library development in MMT, we have to distinguish between the manually written libraries and the generated libraries. This level is usually where the manual work sits. And then we have huge libraries from concrete proof assistants that we translated into MMT. When we translate into MMT, we don't target MMT's concrete syntax. We target its XML syntax, which is based on Kohlhaas's OMDoc format. But recently, especially when we did the Isabelle and Koch libraries, XML became actually not scalable anymore. The individual files just became too big. So now we're working with zipped XML actually, because otherwise, like we have to stream all the files through compression software, because otherwise the files on disk grow to gigabyte ranges where we just can't work with them efficiently anymore. But with that, we were able to take the libraries from 6 major proof assistants and translate them all into MMT compatible XML. That was a huge undertaking. The problem is usually that it's extremely, extremely difficult just to write one of these importers. We always focused on completeness, actually covering the entirety of the language. And that's really hard because every one of these proof assistants has numerous arcane idiosyncrasies, experimental features, legacy features that should be abolished but can't because people have gotten used to them. which make it really hard to represent them in logical frameworks. So basically, for whole, we can still kind of do it in LF. Although already there, the type definition principles of whole don't really work nicely with LF anymore. So basically, all the time we have to come up with new logical frameworks. That's what the +X here represents. Coming up with appropriate frameworks good enough to adequately capture the logics actually used in practice. And that's then where MMT shines, because usually the X that you need is a surprise. So you dig into one particular system like, say, PVS, and you spend a month implementing and communicating back and forth with the PVS developers to truly understand what the various subtleties in PVS actually mean. And halfway through, you realize major complications at the lowest levels, we even have to come up with the appropriate framework feature to actually represent them. That's why, even though we worked on this for 6 years with quite some funding, we were only able to import these systems into MMT. We have not really been able to do much work towards integrating them with each other. So now we have, say, the Booleans of wholelight in MMT, but we also have the Booleans of MESA, and those are currently side by side without any relation between them. We've done a couple of initial experiments on figuring out how we can integrate these concepts across libraries, but that remains a huge problem. Question in the chat. In the previous slide, are functors in the diagram categorical functors or not? So this is a diagram in the category of MMT theories and theory morphisms. So every arrow here is a morphism in MMT. I can go into details of how these morphisms work if there's interest. Additionally, you can think of every node in this diagram as inducing a category, formerly the slice category, namely all MMT theories that extend, for example, first order logic. So any content formalized in first order logic becomes an MMT theory that extends first order logic. So you have the slice category under full. And then via push out, every one of these arrows can be seen as a functor between the slice categories. So you can think of them as functors that translate the category of full theories to the category of S-full theories. So much for the theory. In practice, it turns out push out works only in a few cases as an adequate primitive for representing translations between logics. Current research is going beyond that, figuring out how we can still maintain nice categorical intuitions, but also being able to represent much more complicated translations than compositional ones. Yes, generally MMT formally doesn't distinguish between, oh, sorry, I'm answering the question in the chat on whether there's a difference between logical frameworks and logics in MMT. So generally MMT logical frameworks are just theories like any other theory. So there is no conceptual distinction. There's only the meta theory relation where one MMT theory can designate another one as its meta theory. So the distinction between where was that slide? between the 4 levels here, this is entirely pragmatic on how you use MMT. So these are languages that occur as a meta series of these, and these occur as a meta series of these. Now, there's one difference, so to speak. Usually here you need to inject some rules to get off the ground, to get the semantics of the frameworks. And then usually you don't need to add rules anymore down here. I think that's why in the paper that is referenced here, there's a bit of a difference in the definitions, because I needed to account for the fact that here it's not enough to just write an MMT theory, you have to inject some rules as well. But actually in MMT, you can inject rules at every level. It's just in practice, usually you only need them here, or ideally you only need those extra rules here. I can go into details regarding the kinds of rules that are needed. I can also go into details on the definition of theory morphisms. Okay, let's do that. We briefly do a little bit about the syntax as well. That will probably be. What's going on here? It's not jumping correctly. Okay. So since people in the chat ask about the details of theory morphisms, let me give a little bit more formal details. In the simplest possible incarnation, this is the grammar of MMT. You have constants which are declared in the series, variables which are declared in context, and then complex terms which may bind some variables and which may take some other expressions as arguments. Then, for example, the concrete syntax like lambda x colon a dot t, which you have to want the user to write, in which the parser has to recognize, internally becomes something like the constant lambda binding the variable x and a and taking t as a single argument. On top of that, MMT declares some judgments. First of all, there is a binary judgment between expressions for typing and another one for equality. Both of these are relative to a theory and a context of free variables. And there's a couple other judgments, but these two are really the essence. Now, MMT defines all the system-independent typing rules once and for all, and then every system can add some typing rules of its own. For example, for LF, we add lambda as a constant, so we have to add some typing rules for lambda, like type inference, equality checking, and so on. Each of these are provided as little code snippets, just a couple of lines. And then from that, MMT generates the type checker for the respective languages. In the case of LF, we need about 10 rules. And then from there, we can go to theory morphisms. The general idea is that the theory morphism uniformly represents compositional translations from one theory to another. So they are homomorphic translations from one language to another, meaning a theory morphism from MS to T provides for every constant C of type A in S a term M of C relative to the theory T. And now that must have type M of A, where M of is the homomorphic extension. So this is basically how morphisms are defined for most formal systems. For example, you find that in first order logic in exactly the same way. Institutions are what provided the inspiration of this kind of approaches. Except MMT realized that you can actually do that generically once and for all. And then once you've fixed a meta theory like first order logic, and you've taken the appropriate slice category of theories extending first order logic, you very nicely get the category of first order logic theories and morphisms. So the main idea is we have one huge category of all theories you might want to write down ever, and there are morphisms between them. And then when you define concrete languages, all you have to do is single out the appropriate subcategory. And it turns out we can then use that at all levels. We can represent modular development of logical frameworks in the same way as translations between logics or as morphisms between algebraic theories. So for example, the fact that group extends monoid by just adding the inverse operation and its axioms is a theory morphism in MMT. Inheritance from the superclass to the subclass is a morphism. Semantics, like interpreting first order logic in ZFC, is just a theory morphism in MMT. In fact, the homomorphic extension of that theory morphism is the usual inductive interpretation function that you find when you define the semantics of your logic. Individual models of a theory, like a concrete monoid, can be represented as theory morphisms from the theory into your fixed background theory in which you formulate your semantics. So this could be a particular set theory, a particular programming language, could be a particular proof assistant, depending on what you use as your ground truth to get off the ground. Morphisms are then, models are then just morphisms from the abstract theory into that theory. And lots of logic translations, like negative translation from intuitionistic to classical logic, the other way around, classical to intuitionistic, can be represented as theory morphisms in that style. And it all goes back to the key property that morphisms must preserve all MMT judgments, in particular typing and equality. So let me circle back to some kind of conclusion. What's the most interesting to say next? Maybe I briefly give you an overview of some results. So we've used MMT series as a uniform representation language. I've shown you that. I've shown you that too. Algorithms implemented on top of that. So I've indicated the module system. I've indicated that there's a parser for connecting concrete and abstract syntax, and similarly a presenter to render everything either as text or HTML. I've not shown you, but I can tell you now one of the most advanced results is a generic type reconstruction algorithm, where things like omitted types, implicit arguments, and so on are inferred by MMT. And all you have to do is supply a handful of foundational rules, like 10 rules for LF. We currently have some people doing some initial experiments towards theorem proving or general computation engines. Those are things where MMT can in principle also be used to take the existing techniques and generalize them to language independent levels. It's just that it's hard to compete with the existing systems, and it's hard to enable students to write papers about those things. So we've deprioritized them in the past, but that is something that we're working on. Those are the logical results. We have a lot of knowledge management results as well. That was the original motivation of MMT, that if you fix the whole infrastructure for how languages are defined, you can then implement generic services that every language needs, but that no one wants to implement, like change management, search engines, editing in the browser, all these kind of things, which we can implement once and for all, and often relatively easily in student projects, but which would be extremely difficult to build for any one particular system. Showing you a screenshot of the IDE. Here's an example of the type inference I mentioned earlier. For example, here x and y are given as bound variables without type, and the system notices here that the user made a mistake. This is the HTML browser, in this case of the wholelight library. So here we have the universal quantifier of wholelight. That's one of the libraries that were imported in the OAF project. So for any wholelight type, we have for any predicate on A, the universal quantifier that gives us the universally quantified formula. And now you can hover in the browser, and MMT does the type inference for that system. I saw there's a screenshot on that. No, it's not here. But anyways, MMT should, after selecting a term, you can right-click on it and you get the type inference in the browser. That's a very difficult thing to do because the browser has to be aware of the semantics of your logics, which in the case of MMT works because you can just run MMT as a backend. Here's a very nice mini application that I did for my course. I just used a different set of notations to get proofs rendered as proof trees. In particular, all the intermediate formulas that are derived during the proof, they're all obtained through type inference that happens dynamically in the browser when the proof is shown. And the cool thing about that is it works for an arbitrary logic as soon as you have the rules in MMT. Here's the screenshot for type inference that I mentioned earlier. Here's an example of generic search, again for wholelight. You enter an expression with some free query variables, in this case x, y, and p, and you're looking for expressions of the form x mod p equal y mod p, where mod is one of the constants in one of the theories in the wholelight library. We have a generic search engine that does unification, substitution tree indexing to find efficiently all terms anywhere in these huge libraries that unify with this, and then shows you the results in the browser. These are then two specific theorems in the wholelight library which were found. A current problem is, how can we do this in a way that we find results in multiple libraries? That's what I indicated earlier, that it's really hard to integrate these different libraries with each other. Just minor differences in the type systems often have the effect that it becomes difficult to find results in multiple libraries. So with a modular operator, it's probably still doable, but as soon as you have, already if you have division where systems disagree on how they treat division by zero, it can be tricky to find results across libraries. Our theory graphs became so big, we started visualizing them in 3D. That was a big draw at conferences. And with that, let me go to my conclusion slides. So MMT is quite maturely implemented by now, provides a foundation-independent way to represent individual formal systems. It provides a growing collection of algorithms on top of that, such as parsing, type reconstruction, or HTML generation. Focuses on interactivity, interoperability with other systems, and extensibility wherever I can figure out a way to make it extensible, to make it as easy as possible for users to write other importers, other exporters, other kinds of logical rules. And that leads to a very nice separation of concerns between the person who defines the language, the person who writes support services for that language, and the application developers who use the system then to get other stuff done. I think I should stop here because we said we stop at 50 past, right? And this is as good a point as any if we want to have some room for questions. Let me check the chat again. One question I skipped. Have you done experiments to separate syntax proof systems and models? I'm not entirely sure what you meant by that question. So maybe you can explain.
Yeah, kind of. If you need explanation of my question, I meant that it feels to me that the diagram is getting different levels confused. So kind of things like sorted first order logic versus first order logic, or I mean, on that, can you get back to that MMT theory, the slide that had the picture?
This
that one, yeah. You know, in this third little bubble there, you have models, syntax, and proof systems, right?
Yeah.
And it seems to me that these things are on a different level from the difference between the logic. So I was expecting you to do projections to each one of these things and to try to look at them, to try to find some order on your big diagram of.
Actually, as far as MMT is concerned, they're just normal theories. So this one just happens to be a theory declaring proof rules.
Right.
And this one just happens to be a theory declaring the fundamentals you need in the model. But there is an orthogonality, and it becomes a huge nuisance in practice, especially when you have to think about how to distribute all these theories into files. Like, do you want to put all the proof theory stuff in one folder, or do you put all the first or logic stuff in one folder? It becomes
Well, I was trying to
terribly
say the opposite,
complex,
right? Kind of not to put first orders in one folder, but actually to put all the models together, all the syntax together, and especially the proof systems, because sequence systems are very different from Hilbert systems, which are very different from
Right.
Tableau
And
systems. So
and
that's
it's
the
even
kind of
worse, because you
experiments
always
that I
have
was
things
asking
like-
if you had done.
Yeah. So it gets even more messy in practice. And for all of these, you have then the variant. What else can you prove if you happen to have classical logic? Or like the proof theory of conjunction. Well, conjunction is a bad example, but for every connective, you usually have additional theorems if you happen to be classical. So then the question is, where do you put all those theorems? Do you group all the classical theorems together, or do you group them with the respective connective? And all of them have modal variants, and yeah, so they are all separate in the sense that they're different theories in one huge diagram. But I don't really know how to best linearize them, or how to best map them to this tree structure of a file system.
Right. That was exactly the question, whether there is any kind of lessons learned that you've got on how to linearize things after the event.
No, and I think there's no good answer, because different people in different situations will need different linearizations.
Right. But if you kind of have this whole messy thing, you presumably can do different projections in different directions. And
right, we have those projections so Michael usually likes to call them guided tours, where you say one theory, and then the system gives you the sub diagram that has exactly the material you need to understand that one theorem. That works reasonably well. Michael uses it in his lecture notes a lot.
Right.
If he wants to introduce a particular concept, he can generate the graph of all the prerequisites for that concept.
Cool.
But that usually requires quite a lot of infrastructure on top that has to work, because the user isn't working with the original source files anymore, but with the view onto the source files generated by the system. But yeah, once you have that infrastructure going, you can go crazy. Give me everything relating to Tableau calculus, and then that works quite nicely.
Right. So I mean, I think the question I had, I mean, this was an instantiation of a more general question, because you say down there in blue, library integration is very difficult though. So what I was kind of trying to ask more in general is, how do we kind of, do you have at the moment any great theory of how you're going to try to improve on library integration and library decomposition, which is what we are talking about now, right? I mean, I assume that library integration, you mean picking up the PVS theorem library and putting together with the wholelight library.
Right, that would be
so I want
nice thing to do, yeah. And
on the other hand, I also think that we want to kind of do decompositions, right? Kind of, here you're decomposing, saying wholelight is different from Misa, and I kind of separate them and have two bubbles underneath. So the question is, and maybe someone will come and say, no, that's not the right way of separating. It's they both have a Boolean saying, so kind of that's how I want to separate. So whether you have any new big insights along these lines of integrating and decomposing those libraries.
Lots of insights, lots of experiments, but no ready to use instructions for how you can do it. Like, let me give you just one data point. Already in Coq alone, there's like, I don't know, 5 or 10 different versions of the real numbers. So it's not even just integrating across libraries. Even within the library, it's a mess. And the maintainers of each library are struggling to have some semblance of order in there. The one thing I can say is systems should strive to follow the little series approach of formalizing every concept in the smallest context in which it makes sense. Unfortunately, systems don't do that in practice. So of the big proof assistants, actually the reason why we have IMS on this list, even though it's not a big proof assistant, is it's the one system that systematically uses little series. Coq, PVS, and Isabel supported in principle, but then in practice, it's not used that much. Isabel type classes are used a bit. PVS does use some modularity for the algebraic hierarchy in similar situations, but overall, it's not used enough, I would say, in all of these systems. And that means if you just take any theorem from any one of these libraries, the dependency that you need will be everything in that systems library, down to the foundations. And just disentangling that to say, hey, this theorem about arithmetic really only depends on the Peano axioms, and we can abstract that away. Then we map the Peano axioms to some other proof assistant, and we can transport that theorem over. Most systems just don't offer that kind of infrastructure. So very often, the best method would be to go into these various libraries and restructure them systematically to have more modularity in the libraries. Right. The Gilles Doek's group around Deducti, they've actually kind of done that a bit for a tiny arithmetics library. And then they were able to port that one into the different theorem provers. So as an experiment, it showed the method, but it just, we don't know how to scale that up to the huge libraries that we have.
Well, thank you. That's very helpful. Thank you.
Yeah, let me interrupt. I think we should thank Florian. Everyone can unmute and clap or just put the symbol. Thanks for the great talk, Florian. And I think we'll cut the live stream, and then anyone who wants to stay and ask informal questions, please feel free. So thanks again.
Okay, great. Thanks for having me.